Welcome student. This is the second lecture of similarity transformation. So last class we have rigorously discussed the concept of similarity transformation, why it is called similarity transformation. Then we have understood what are the utilizations of similarity transformation, and then we have studied about the generalized method of similarity transformation. So just to remind you that what is similarity transformation is, that is simply you can understand like this, that we have a realization, simply we have a realization x dot equal to ax plus bu, okay, and the output equation y equal to cx. Now what we want that we want to create another realization from this given realization. So this realization is given to you, and we want to transform this system to a new coordinate where the x and x bar will be related like this, that is x bar will be related with the old coordinate by t inverse of x, okay, where 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 T is known as transformation matrix. T is known as transformation matrix. Okay, so we are assuming that this we can build this T, or we can have this T such that the old coordinate x or old state x is related to the new state x like this. So if they are related like this, then we can write the new coordinate system, that is by differentiating this relation. So if we differentiate this relation, we can get that T inverse of x dot, and x dot we will replace by the relation what we know. So it will be T inverse of ax plus bu, and we expand it. If we expand it, then we are getting T inverse ax plus T inverse bu. But you see, this is in the new coordinate, not in a new coordinate, it is x. So x must be replaced by x bar. So that's why T inverse a T into x bar plus T inverse B into u. So now you can think that this is the new A, that is A bar, and this is the new B, that is B bar, okay, and so this is the relation what we got in the new coordinate system x bar dot is equal to, this is the state equation. Similarly, we can derive the output equation, that is y equal to c into x, and x we can write c into t x bar. So this is the new c bar matrix what we have, okay. So now what is our intention here? The intention here to get some canonical form of A bar, B bar, C bar, and for that we want to build this T matrix, okay, we want to build this T matrix. So now the first thing what we want to do, that one, that is diagonalization. Means what? Now if any realization is given, can I build a T matrix, or can I find a T matrix such that non-diagonal form or non-diagonal realization can be transformed to a diagonal realization, okay. And that's why today's topic is diagonalization. So the question is, can we use similarity transformation to create realization which are simpler than the original? Okay, so we have a non-diagonal realization, and we want to transform to a simpler form of the original, and that is actually diagonal. Because why it is called simpler form, diagonal realization, it will be clear to you, because from the diagonal representation many things can be many characteristics of systems can be known if the system is represented in diagonal form. Okay, that we are going to discuss today also. Okay, so can we diagonalize? So that's the same question we can ask, that is, can we diagonalize any realization by similarity transformation? Okay, but the answer is no in general. Let us investigate further. Means, what is the meaning of that? Means, suppose if any realization is given, and if we want to transform that realization to the diagonal one, always it is not possible. Okay, so some restrictions are there. So we want to state that restrictions, or on the basis of what condition actually this diagonalization process can exist. So this reduces to the following question: is there a matrix T such that A equal to, sorry, here it will be A bar, it will be A bar, it is a mistake, A bar will be equal to T inverse of AT is diagonal. Okay, so can we build a T matrix such that A bar will be equal to T inverse AT? Means, here you see what we have deduced here. So now what we want that this A bar we want diagonal. Okay, and now this the question is that, can I build this T matrix such that any form can be transformed to the diagonal one? Okay, so now we are going back to the slide. So now we are going to state some fact that when this diagonalization is possible. From the linear algebra, fact 1 is telling that a n by n matrix A is diagonalizable if and only if it has n linearly independent eigenvector. Means, if suppose a matrix is given to you and it has been asked that whether A can be diagonalizable or not, only when it will be diagonalizable if it having n linearly independent eigenvector. Okay, the dimension of A we are assuming that is n by n matrix. Okay, and most important thing you have to remember that here for our purpose the diagonalization we want to do over the real numbers. So that's why we will modify this fact 1. A n by n real matrix A is diagonalizable over the reals, means all the elements of the A matrix will be real if and only if it has n linearly independent real eigenvectors. Okay, which is equivalent to the fact 3. What is that? Now, an easier way to check the condition is that through the sufficient condition that n by n real matrix A is diagonalizable over the reals if it has n real distinct eigenvalues. So this is the condition you can remember. The fact 3, if you remember, then it is fine. In GATE also I have seen this kind of multiple choice question came, that when the diagonalization process is possible. The answer is, when you will find that n real distinct eigenvalues are there, then A matrix will be real diagonalization over the reals, means all the elements of the A matrix will be real. But in general, A matrix will be diagonalizable if it has n linearly independent eigenvector. So if a matrix has been given to you in your exam and it has been asked that it is diagonalizable or not, you can assume that actually we are telling about the diagonalization over the real. And how you will check that one? Now, if you found that all the eigenvalues of the given A matrix are real, then the diagonalization is possible. Means a T matrix exists by which you can transform the non-diagonal form to the diagonal one with this relation, that is T inverse AT. So A bar will be in the diagonal when you do the operation T inverse AT. Okay, so that's why in the next question we will ask that how this T matrix will be built. Okay, so now we will start that. Assume that A has, because this is the criteria, assume suppose A matrix is given to you and it has been asked that you build the T matrix such that transform A bar will be diagonalized. Okay, so assume A has n linearly independent eigenvectors, that is T1, T2, Tn. So these are all column vectors, so don't be confused. T1 is a column vector, T2 is a column vector, Tn are the column vectors. Okay, and from the definition, how this eigenvectors you have found out. Now with this relation, a into ti is equal to lambda I into ti, where lambda i's are the corresponding eigenvalues. So if you have the eigenvalue lambda 1, then how you will find out? Now a t1 equal to lambda 1 t1, and t1 having n number of elements, and it is a column vector. Okay, so now what we will do, we will build a matrix by picking this t1, t2, tn. Okay, we will stack this column vector. So tn by n with t1, t2, tn as its column. So t is equal to t1, t2, tn, and t is a capital T is a matrix whose dimension is n by n. Okay, and all the vectors, this t1, t2, t1, tn, all these column vectors by which this capital T has been built, all are linearly independent. So that's why T is invertible. Okay, so this is the very important thing you have to remember, because here the T matrix, the transformation matrix, what you are going to build, one key property is that must be invertible. Otherwise you cannot find out the A bar by the relation T inverse AT. Okay, because T inverse you have to take. Fine. Now what we will do, we can write AT, that is A into capital T. Already T we have defined, these are the column vectors t1, t2, tn. So AT will be A into t1, t2, tn, and this multiplication is also possible because A is a n by n matrix and t1 is a n cross 1. Okay, so we can multiply that one, at1, at2, atn, and now you try to see from the definition of the eigenvectors, ati is equal to lambda iti. So at1 can be replaced by lambda 1 t1, at2 can be replaced by lambda 2 t2, and atn can be replaced by lambda n tn. And this equation can be written in the following way, that is t1, t2, tn, which is a n by n matrix, and this is also n by matrix, by keeping all the eigenvalues at the diagonal. So lambda 1, lambda 2, lambda. So this is the diagonal representation. So we can name it a bar. So now you see, we can write at equal to t a bar. So a bar we can get t inverse at, and that will be the diagonal representation of the given system A. Okay, and here important to remember, all the diagonal elements are the eigenvalues of the A matrix. All the diagonal elements are the eigenvalues of A matrix. So now we will try to understand the topic what I told with an example. So now consider a system x dot equal to this. So it is a non-diagonal system has been given. Now the question has been given, diagonalize the above system by constructing suitable T matrix. So we have to find out a T matrix of this given system such that this given system can be transformed to a diagonal one. So now what we'll do, we will go step by step. So first step is that we will calculate the eigenvalues, because if we want to diagonalize it, the condition is that all the eigenvalues must be real and they will be distinct. Okay, so step 1, compute eigenvalues. So here eigenvalues we are finding that 1, 2 and minus 1. Okay, once the eigenvalues has been computed, then we have to compute in step 2 the corresponding eigenvectors. Means, suppose if I want to compute the eigenvectors of the corresponding eigenvalue lambda 1 equal to 1, then this relation will be helpful. ATI equal to lambda ITI. So A, then Ti having 3 components, we have taken the three elements. So T11, T12, T13 equal to 1 into T11, T12, T12. So this is a linear system and you can solve it. If you solve it, you will get the eigenvector 2 minus 2 1. So this is the eigenvector corresponding to lambda 1 equal to 1. Similarly, we can calculate the eigenvector to the eigenvalue 2, that is 0 1 0 transpose. So it is a column vector, and for the -1 eigenvectors are 0, 0, 1 transpose. Okay, so these are the step 2. You have calculated the eigenvectors. Why? Because these eigenvectors will form the T matrix. So T will be the column of T matrix will be the eigenvectors. So 2, -2, 1, 0, 1, 0 and 0, 0, 1. And next step will be we have to compute T inverse. So we will compute the T inverse, and then finally we will compute T inverse AT. And if you do this operation, you will find that it will be diagonal, and all the diagonal elements will be the eigenvalues of what you have computed, 1, 2 and -1. So this is the complete description or steps you have to follow to diagonalize a system. Okay, but one shortcut method is there only if the original matrix in a controller canonical form. Okay, in that case no need to compute the eigenvectors, directly you can compute the T matrix. Okay, so how you can do that one? Now, if A is in controller canonical form and A has distinct eigenvalues, then the T matrix will be in the form of this. All the first row will be 1, 1, 1. Then second row will be the individual eigenvalues, lambda 1, lambda 2, lambda 3, lambda n. And then it will be lambda 1 square, lambda 2 square, lambda 3 square, lambda n square, and this will go up to the power n minus 1, where lambda 1, lambda 2, lambda n are the eigenvalues of A matrix. Okay, so this T you can follow the same method, okay, by calculating the lambda 1, lambda 2, lambda 3, lambda n, then eigenvectors, and then if you stack the eigenvectors you will find that they will be in this form. So that's why one clue is that if the A matrix is already in controller canonical form, directly you can calculate the T matrix. Okay, so this is the clue. Sometimes it will be useful to you in your exam. Suppose fortunately if you get A matrix where the diagonalization has been asked, directly you can write this T matrix. Okay, so that's why to understand this theory, here one example I have taken. So x dot equal to Ax, where you are finding that already the A matrix is in controller canonical form. So first you have to calculate the eigenvalue, that is -1, -2 and -3. They are distinct and real. So now T will be 1, 1, 1, lambda 1, lambda 2, lambda 3, and lambda 1 square, lambda 2 square, lambda 3 square. Why? It is up to n minus 1. Here order of the system is 3, so the power will go to n minus 1. You see here it is n minus 1. So it is 1, 1, 1, -1, -2, -3, 1, 4, 9. So now this is your T matrix. Then you calculate the T inverse, and if you calculate the A bar, then you will find that it will be -1, 0, 0, 0, -2, 0, 0, 0, -3. Okay, so now we have clearly understood that how the diagonalization can be done, means how to build the T matrix if any non-diagonal form has been given. Now the second question is that why this diagonalization we can do, or we will do. Okay, because you see at the beginning one question has been asked that can we transform using similarity transformation which is simpler than original, means what simplicity we can expect if a system is represented in a diagonal form. Okay, one thing you can very easily conclude, that first property or first thing what you can understood, that if the system is in diagonal form and you know that all the diagonal elements are the eigenvalues of the A matrix, then you can comment about the stability of the system, internal stability of the system, and you know that if the system is asymptotically stable, then all the eigenvalues of the system should be located at the left half of the S plane, or it should have negative real part. Okay, so if a system is represented in a diagonal form, and if you see that all the diagonal elements are at have negative real part, then you can say that system is asymptotically stable. And another advantage we are going to tell you, that easier way to calculate e to the power at. Okay, so if you can remember, we have in our class we have stated till now two methods to find out the e to the power at. First method is Laplace transform approach, second approach using Cayley-Hamilton theorem, and third thing now we are going to tell that how e to the power at can be calculated using diagonalization approach. Okay, so now suppose if already a system, suppose if you have diagonalized a system. Okay, just now we have taken the example where a bar you got 1 0 0 0 2 0 0 0 minus 1. So this is the transform system which is in a diagonal form. Now if I will ask you to find out the e to the power a bar t, means the e to the power means the state transition matrix of the diagonalized system, then it is very easy. You see, simply e to the power a bar t will be e to the power t, e to the power 2t, and e to the power minus 2t. Okay, so no need to do that that partial fraction expansion and something some more complicated step. So now thing is that if a system is transformed in a diagonal form, then e to the power a bar t is easy to calculate. But here one thing you have to remember, this e to the power a bar t is the for the transform system, not for the original system. So if you want to calculate really for the original system, then some more calculation you have to do. What you have to do now that we are going to discuss in this slide, that how the e to the power a bar t and e to the power at is related. Because remind that this a bar is the diagonalized system, means it is not the original system, and for that e to the power a bar t is easy to calculate. But how this e to the power a bar t and e to the power at is related for the original system, how it is related. Okay, to understand that, it is very easy to understand. You see that a bar, how you have calculated the t inverse at, where a bar is the diagonal. Okay, and if a bar is in diagonal, then e to the power a bar t is easy to calculate, so it will be simply e to the power lambda 1 t, then e to the power lambda n t. Okay, now a is related. How the a is related? Now we can write that t a bar t inverse with this relation. You see, this is the relation what we got. Okay, so now so this is the relation. From this relation what we are getting, a equal to t t a bar t inverse. So now e to the power at, from the relation we know that it is I plus at plus 1 by 2 factorial at square. Now we can write this a by this relation, that t a bar t inverse into t, then a is replaced by this relation, and I is t into t inverse we can write. Okay, and then we have expanded this square. Okay, just we have removed this square by writing t a bar t inverse, t a bar t inverse. Now from here it is very clear that we can write this one as t into I plus a bar t plus 1 by 2 factorial a bar t whole square plus t inverse. So this is basically e to the power a bar t t inverse, t into then this is the e to the power, this part is e to the power a bar t t inverse. So now e to the power at is related by this relation t e to the power a bar t t inverse. It means that once you will calculate e to the power a bar t, then actually you have to do this operation, that is t into e to the power a bar t into t inverse, to get the original e to the power at. So this is the theory, and you have to remember this relation. So now once you have calculated this e to the power at by this method, then you can calculate the state also xt. Okay, or if you calculated the x bar t by the diagonalization approach, then xt you have to calculate by the relation t into x bar t. Means these are all in transform domain, and you have to calculate it for the original domain by this relation. Okay, so now whatever we have discussed till now, we will try to do with an example, the same example what we have taken for the diagonalization. Suppose it has been asked, compute e to the power at using modal decomposition or diagonalization for the following system. Okay, so you have to compute e to the power at. The method till now what we have discussed, it is also known as modal decomposition or diagonalization approach. So in your exam, if it has been asked that it is e to the power at, you have to calculate using modal decomposition approach, then you have to use this method. You cannot use other two method what we have already discussed. Okay, so now what are the steps you have to follow if you want to compute e to the power at for this system using diagonalization approach? Now first you have to compute the diagonalization matrix T. The T already I have shown you how to calculate or how to build the T matrix for this system. Then you calculate T inverse. Once you know the T inverse, then you know that what will be the A bar. A bar will be T inverse, that is 1 0 0 0 2 0 0 0 minus 1, and then you can compute e to the power A bar T. It is very simple. Simply e to the power T, e to the power 2t and e to the power minus T will be the diagonal elements. All other elements will be 0. Now we will compute the e to the power at for the original system by this relation. So we have to transform it back to the original domain by the operation T e to the power A bar T into T inverse. So now this is the T matrix, this is the state transition matrix in the transform domain in the diagonal for the diagonal form, and this is the T inverse. And if you do this operation, the ultimate, the expression what you will get, that is the state transition matrix for the e to the power 80. So in this is the process by which you can find out the e to the power 80 in this process. Okay, so now till now we have understood what is the utilization of the diagonalization. First thing is that if you diagonalize a process, a system in from the diagonal form directly, you can comment about the stability of the system. Second advantage what we have learned, that we can compute e to the power 80 very easily if we use the diagonalization approach. Okay, so that's why here it is summarized that 3 ways to calculate e to the power 80. We can calculate using Laplace transform technique, using Cayley-Hamilton theorem, and using modal decomposition or the diagonalization. Okay, so now to understand the another important aspect of diagonalization, we have taken another example where the system is in the diagonal form. Okay, so this is the A matrix, this is the B matrix, and this is the C matrix. So this is the A matrix, this is the B matrix, and this is the C matrix. So now if it is like that, then we can very easily write what is x1 dot dynamics, x2 dot dynamics, x1 dynamics, x2 dynamics, and x3 dynamics, and the output equation. And this, if you see this equation when it is in diagonal form, you see it is called decoupled form. Why it is decoupled form? Because this x1 dynamics, x1 bar dynamics only depends on x1 bar. It is not depending on x2 and x3, so it is decoupled. So x2 bar dynamics only depending on x2 bar, so it is decoupled. x3 bar is only depending x3 bar. Okay, now what is the advantage? Now if it is in this form, now you can write what will be the solution directly, because the solution of this system will be xi bar t will be e to the power lambda it into xi bar 0 plus 0 to t e to the power lambda it minus tau bi u tau d tau. Means if I want to calculate x1 bar, we can use this relation. If we want to calculate x2 bar, and if we want to calculate the x3 bar, easily we can calculate. And if it is like this, then you can see that the first part, which is the initial due to the initial condition, which is also known as zero input response. From this you can comment about the stability. Stability means whether this particular state is going to diverge or converge. By looking the sign of lambda I, you can comment. Okay, you can, if it is plus, then you can say that that particular state is going to diverge, and if it is negative, then you can say that particular state is going to converge. So the stability is going to depend about the sign of this. Okay, and most importantly, the zero state response, which is involved with the input part, then we can see, we can, if it is in a diagonal form, and then we can tell that actually which mode can be influenced by the input and which mode cannot be influenced by the input. That also we can conclude. And to understand that one, we can consider the example we have given for the stability. Okay, you see in this example, this example already in the discussion of internal stability we have taken. Okay, so A, B, C, the A is in already in diagonal form. Okay, now when you are writing the particular x2 dynamics, because here x2 dynamics is important, because you see x1 dynamics is stable, x3 dynamics is also stable. What about the x2 having the speciality? You see the e to the power 3t. So here this particular eigenvalue is positive, so that's why this part is going to diverge. So that's why this x2 dynamics is unstable. Also you see this B matrix is the second element of B matrix is 0. So due to that, this part is also going to be 0, because B2 is going to be 0. So now what will happen if B2 is going to 0? Because what is the meaning of that? If the B2 is 0, means this particular mode x2, okay, cannot be influenced by the input. Already this mode is diverging, it is unstable. So now question is there any control exist by which we can control this x2? The answer is no, because no input exists to influence this x2. Okay, so that is visible only if it is represented in diagonal form. So that's why here you see at that time we have written the mode according to lambda equal to 3 is said to be uncontrollable from U. Because why it is uncontrollable? Because it is unstable. So these two things are very clear to you have to understand, because later the topic will be the controllability. This is unstable, it is fine, but is it controllable? No, it is not controllable, this particular state, because there no such input exist. Due to this B2 element is 0, so there no such input exists by which you can influence this x2. Okay, so that's why it is uncontrollable, not only unstable, it is uncontrollable also. Okay, and the third example also you will find that this C element, this one is 0. Okay, and if you see that we have written that the output y equal to C1 x1 plus C bar into x2 plus C3 bar into x3. Okay, so now here from the output equation you can see that this element is 0, and if this particular element is 0, means the particular state, that x2 cannot be construct by looking the output. So that's why here the mode according to the lambda equal to 3 is said to be unobservable from y. From y actually that particular mode cannot be seen. So that is the concept of unobservability or observability, we can say. So these are the things you can easily conclude if the system is transformed in diagonalization. So today now we are going to finish this lecture So now what we have learned, now today we have learned how to build. The first thing is that for what condition we can find out the, or we can diagonalize any non-diagonal realization. We found that if we have the n number of real distinct eigenvalues, then only we can find the diagonalization over the real. Okay, second thing is very important, how to build the T matrix for the diagonalization. For the general case we have discussed, and if already the system is in controller canonical form, then directly we can build the T matrix. That process I have also discussed. Then I have discussed mainly what is or why the diagonalization process is so important to us. First thing is that we can comment about the stability if only the system is in the diagonal form, because diagonal elements are the eigenvalues. Okay, second thing we have observed that the calculation of e to the power at becomes simple if the system and if we follow the diagonalization approach, and the steps already we have seen. And then last of all we have shown that we can see that which mode, means which state will be controllable, or which along with the stability which mode will be non-controllable. That also can be easily verified or easily concluded from the expression. And also we can which state can be observed from the output and which state cannot be observed from the output, that also can be easily visualized if the system is represented in diagonal canonical form. So this is the second part of similarity transformation. So next class we are going to discuss, that is the last class for the similarity transformation. Next class we are going to discuss two important form how we can find out, that is controller canonical form and observer canonical form. Means the thing is that same way, if any form is given or any realization is given, how we can find out the controller canonical form, and if any form is given, how we can find out the observer canonical form. Okay, so this we are going to discuss in the next class. Thank you.